Okay.
Yeah. So maybe subsequent settings, I'll set it that yeah, it's recording now. Go ahead.
It's recording. Okay. 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 All right. Okay. So
and those that are coming in, just be on the lookout. Those who are in the waiting room. So once you click on the participant list, you will see a list of those who are already in and those who are waiting. Just click on and admit them in.
Okay. Okay.
Yes.
Okay.
Yeah, thank you.
Okay. That's fine. Okay. So before that, I was talking about the processes of converting living organisms to fossil fuel that we now extract today. Through the extraction processes of crude oil and all of that. So we extract this and then we refine them, to a final petroleum product like PMS or diesel. And the reason why we do all of this is to power our economic activities. Okay. Now, this is where the problem is. By nature, God has designed the system that this energy comes from the sun, it passes through the tree, passes through the human, and is then being sequestrated, it's being stored, below the earth. But because of human activities, we have to now extract this energy in the form of crude oil, and then we use to power our economic activity. Now, here is what actually happens. Because the sun is already sending enough energy that we require to meet our daily activities on Earth, then plus the energy that we extract from the Earth to also power our economic activities, it now end up hitting the Earth and then making it hotter than it should be. And that is what we now refer to as climate change or global warming. Global warming eventually leads to climate change. So now, this is the problem why climate change is one of the biggest problems in the world and why the push for renewable energy is happening by all means. So energy does not remain in the same form always. It causes change. Energy itself changes from one form to another. And during this change, energy is always conserved. What does that mean? It is not created anew or destroyed. It is known, this process is known as the law of energy conservation. So in other words, the law of energy conservation states that energy cannot be created or destroyed, but can be converted from one form to another. I'm sure many of us know this, so this is just a reminder. So let us look at the energy and power. Earlier at the onset, I said we shouldn't mistake energy with power. They are two different things. Okay. So energy is the capacity to do work. So in other words, energy is force over distance. When you push an object, the force you apply to that object plus the distance you've been able to move that object is what is known as energy. So in other words, if you push that object and it didn't move, you've not dissipated any energy. Okay, and the unit of that energy is joule. Joule is a unit form of thermal energy. Okay, so we'll see how we can now convert this joule to maybe form of electrical energy and other forms of energy. So now this is the relationship between energy and power. Okay, so power is energy divided by time. Okay, when you make energy the subject of the formula, what you're going to have is power times time. Okay, that's if energy becomes the subject of the formula. Okay, please note this formula. This relationship between power and energy is very, very important. I've read some reports where people mistake, people put power in the place of energy, or they put energy in the place of power. They are two different things. Okay, so watt itself is power. Okay, and remember I said that joule is a unit of energy. Okay, so if you now divide that joule by time, which is second, you have the unit of power, which is joule per second. So remember I said that if you now make energy the subject of the formula, what you're going to have is power times time. So the unit of energy is watt second, not watt per second, watt second. Whereas the unit of power is joule per second. We have to take note of this little units formations so that we can always communicate effectively, maybe in our report or in our speaking. So now joule, what joule actually means is 1 Newton over a distance of 1 meter. Remember when I defined energy. I say if you apply a force on an object and you move it over a distance. So that's what actually joule means. So force times distance. Okay. So joule is a unit of thermal energy. I said this earlier. Okay. So amount of watts in 1 hour is also energy. You know, I said watt second is energy. Okay. So when you now divide it by 1,000, which is a kilo, it becomes kilowatt hour. You now also convert seconds to hour. So this is the most common unit that we all know, kilowatt hour. Your electricity bills comes in kilowatt hour. And I'm sure we understand how we arrive at kilowatt hour, which is power times time. Okay. So power now let's come to power. Power is the rate of energy. Okay. So power tells you how fast or how much you're dissipating energy. That's what power means. Okay. So when you divide energy over time, you have your power. So when 1 ampere is pushed by 1 volt, okay, that is the rate of energy. Okay. So power can also be defined as voltage times current. Now I'll get this, in a little bit when we will not begin to talk about some other forms of basic formulas for power. But just also know that power is also voltage times current. But mind you, this is not the real power. This is the apparent power. I will come to that, but just I just want to bring it here so that when I come to that, it might be easier for us to understand. So, like I said, power is a measure of how fast energy is used. So, how fast you're dissipating energy is what your power is truly is. And I told you that the unit of power is joule per second. So 1 kilowatt hour is equals to 3,600 kilojoule, which is equal to, now when you divide this 3,600 kilojoule by 1,000, you convert it to megajoule. Okay, we divide it by another 1,000, you convert it to gigajoule. So you might not just worry so much about it. You can always make references to these pages whenever you're doing your calculations and all of that. But it is important you remember the relationship between power and energy. Power is energy times time. That is very, very key. So this is further units of power and energy and all of that. How you begin to move from 1 watt second up to the point you have terawatt hour. So this is just a factor of 1,000. You keep, dividing by 1,000, then you keep increasing the factor. That's what this page is all about. So let's just do a little exercise to put this into perspective. So the question is, what is the cost of 1 kilowatt? What is the cost of 5 kilowatts continuous operation in 1 year? I take that again. What is the cost of 5 kilowatt continuous operation in 1 year? Now, a hint to that question is, in a year, you have 365 days. In a day, you have 24 hours. So when you now, if you want to calculate the total number of hours, remember our energy is kilowatt hour. So you want to calculate the total number of hours for the year. So you now multiply the number of days times the hours per day. Okay, so that will give us 8,760 hours per year. Then another hint is that the cost of electricity is 0.1 US dollars per kilowatt hour. So I don't know if we can just do a little quick calculations on what the cost of 5 kilowatts continuous operation in a year would be before I show you the answer. Can we just do that in 30 seconds, please? Oh, I can see an answer from someone. J. John, 4,380. Okay, let's see if he got it correct. Yeah, so that is the answer, 4,380 USD. Very correct. So what we actually did was the power, which is the 5 kilowatts, times hours, which is 8,760. Then you have 43,800 kilowatt hour in a year. So we now multiply that kilowatt hour by the cost of unit energy, which is 0.1 USD. You have 4,380 USD. Very correct. Thank you, John. And every other person that got it right. I don't know if there are more responses here. Please, can we all mute our mic if we are not speaking? Unless you have a question, then you can unmute yourself, please. Okay, so okay, another test question. What is the difference between kilowatt and kilowatt hour per hour? If you want to answer, please, you can unmute yourself and then speak to your mic. Is anybody going to make an attempt?
Hello.
Hello.
Yeah.
Rita?
This is Rita.
Okay.
The question, first of all, I would say the question seemed a bit confusing because I am more familiar with the difference between kilowatts and kilowatt hour, which is usually energy, like energy demand and energy consumption. So I'm wondering, like, I got a bit confused when I saw per hour, like kilowatt hour per hour.
Okay. Okay. So thank you for that, and that's the whole reason for putting this up so that we don't get confused. Okay. The whole essence is for us to be able to interpret what these things are when we see them. Okay. So when the first one, which is the kilowatt, is telling us, it's talking about power. Okay, so it's talking about the rate, of energy consumption. So if you have a higher power, meaning that the rate of energy consumption is also faster, it's higher. Okay, so that is power. Then the second one is referencing energy, not power. So what that means is that you consume certain amount of energy in 1 hour. That's what it means. You consume certain amount of energy in 1 hour. So if you have 24 hours, you're reducing that 24 hours to 1 hour. Okay. This can also be said kilowatt hour per day. So what that means, what that tells you that you're consuming certain amount of energy in a whole day, which is in 24 hours. But kilowatt hour per hour means that you're consuming. So if, for example, if I have 10 kilowatt hour per hour, what that tells me is that I consume 10 units of energy in 1 hour. That's what it is. Okay. It is tricky because you can cancel out the hours and then you're left with kilowatts and then you just have power. Okay. But it's a way of representing energy, okay, in an hourly basis. Rita, is that okay? Is that clear?
No, but of course it's something. Okay, maybe it's just me trying to put too many things together. But what I was like looking forward to here was, I quite agree with you, is the difference between power and energy.
Okay.
Right. But I was also looking forward to you mentioning demand and consumption. Energy demand and energy consumption.
You're absolutely correct. Demand is power. Consumption is energy. So you're correct. Is that clear?
Hello?
Hello. Yes.
Okay, sorry. Maybe I just want to look at it from the other mathematical point of view. So when you say kilowatts, we understand what that actually means. That's energy or power as it may be here. But when you say kilowatt hour, to me that is energy consuming in 1 hour. But when you say per hour again, it's like you're referring back to kilowatts. So mathematically, the hours can cancel out. So what you have is just kilowatts. I don't know whether I'm just getting. I think that's what I can see here. So they're actually the same to me.
Okay. Yeah, you raised a valid point, and I said this: if the cancel the 2 hours, you're back to energy. Okay. Now the reason why we have kilowatt hour per hour is sometimes you might want to aggregate. Okay, you want to how do I put it? You want to quote the certain demand of people, but over an hour, you want that demand to be more like a constant value. Okay. So I'm trying to put this into perspective. I don't want to go into regulation because there are certain aspects of regulation where it is quoted like this. And I know when we reviewed that regulation, we had some little discussion over this. Okay. So it's simply saying that, look, if I say that I want Rita and John, both of their energy consumption put together to be 10 kilowatt hour per hour. Rita and John, I want their energy consumption to be 10 kilowatt hour per hour. What that simply means that I want you both of your energy consumption to be 10 kilowatts without changing for the next 1 hour. I don't know if that's clear. I want the power demand for Rita and John to remain at 10 kilowatts. It's not going to drop to 9, it's not going to increase to 11. It's going to remain at 10 kilowatts for a complete 1 hour. That's what that kilowatt hour per hour is saying. If you look at it from a mathematical point of view, yes, you can cancel the hours and you come back to power. And which is the same thing I said, that I want both of your energy demand to be 10 kilowatts. I don't want it to go down. I don't want it to go up. Just remain at 10 kilowatts for the next 1 hour.
Okay, I think it's quite clear now. So if you look at it at maybe on an average point of view, that is clear. Because if you have maybe a 10 kilowatts power, and in per hour, in 1 hour, consumption in 1 hour, which is the energy now, it will be same kilowatt hour. But if you want to actually define it by hour again, so depending on how many hours you have, so it may be like an average over a certain period of time. The energy may be in a certain period of time. So I think that's quite clear.
Okay. So thank you very much for the observations and contributions. So we proceed.
Can I chip in something?
Okay, please go ahead.
Yeah, so what I can see there, kilowatts is power, kilowatt hour is energy. Then kilowatt hour per hour also goes back to kilowatts. But in our common usage or in terms of practical application, when energy is being charged, is kilowatt hour that is usually used. Exactly. So I think some of these units are actually derived based on the convenience of using them in the market.
Exactly.
So
and if
you
you
charge energy per hour rather than charging them per second. And so the idea of kilowatt hour per hour is just a way or a convenient way of trying to measure how much energy a given unit or a facility or a building is consuming for an hour. Exactly. So we should look at it more as a measure or a means of trying to do the marketing part.
Okay. Yeah, I totally agree with you. And it's actually in that context that it was used in the regulation that we are talking about. Okay. So I hope we are clear on that. I just brought it up because I know like Rita said, it's confusing, but I just brought it up so we can also, put on our critical thinking cap, as we proceed. So thank you very much for your contribution. So now, talking about renewable energy sources, we have the solar radiation, we have the hydro, we have the wind, we have the ocean-related energy, which is the wave, tidal, thermal, salinity gradient, and all of that. We have the biomass, we have the crop, wood, forest residues, and the waste. Then the biogas, which is the decomposition of biomaterials in the absence of oxygen. We have the geothermal extraction of heat from the earth's crust, for power generation of whatever form of energy you want to convert to. So all this we can always read up and all of that. So we have the non-renewable energy resources. You have the chemical, which is the fossil fuel, coal, oil, gas, and all of that. We have the nuclear energy, which is uranium. We have thorium and some other forms of nuclear energy. Okay, but for this purpose, uranium is just fine. So let us look at thermodynamic basics. Thermodynamic.
Hello? Hello, can we hear him?
I think he's frozen.
Okay.
Yeah.
Yeah.
Frozen.
Until he comes back, and let's continue. I was almost pushed to remind us that we are trying to lay a foundation. This might not be anything for some of us, but let's just be patient, because it's good that we lay this foundation and all of us will be on the same page. After that, we will move in at a higher pace. So I think we lost. Let me just see if I can find him. It's funny, yeah. This is something that if you are doing online training in Nigeria, you must factor in this issue. Sometime, I think in the last 2 weeks, network has been, I don't know what's happening. It's quite funny. So let me just try to step in for him while we're talking about energy and electrical basics. We're in thermodynamics. So while he comes in, my section today is supposed to be from the auditing proper, how we go about the auditing thing, because that's the idea of this module. The other module that will come in with other things. So thermodynamics. Okay, these are all the foundation, just to remind us of what we're talking about. Okay, heat conduction, heat transfer by molecular contact, mostly effective in solid materials. Of course, we have conduction and we have convection. So when you talk about conduction, we are referring to there must be contact, and this is mostly obtainable in solid materials. Then we have convection, which is heat transfer through density difference, mostly effective in liquids and fuel. So in most HVAC systems, cooling and refrigerating system, you see more of using convection. And when you talk about other forms of energy, you'll be looking at conduction. Then thermal radiation says heat transfer by wave action. In this case, no material is required, and usually occur in space. So here we have like the energy from the sun, for instance. It's usually occur in space, and there's no transfer medium. There's nothing to transfer, unlike in convection, where the medium of transfer is liquid or gases. And then, of course, in the conduction, we're not talking about solid materials. So these are the three major modes of heat transfer in any thermodynamic system.
A quick one.
Yes, sir.
For convection heat transfer through density difference is when you have natural convection. Okay. So there are cases where you have forced convection heat transfer, okay, which is not based on density difference. Okay. So there are actually two modes of convection heat transfer. So you have the natural and forced convection. So
all right. So, but both of them are still under convection, I guess.
Yeah, they are both convection type, but the one based on density, which is buoyancy, is actually natural convection.
Okay.
A forced convection heat transfer, which doesn't depend on density difference.
It's okay. Thank you for that.
Yeah.
So please, I also urge other members of the class to come in. Okay, Chima, are you back?
I'm back, but my presentation is not up yet. I don't know what happened. I looked
I will share with you. I think the system logged you out, so I'll give you back power. Are you ready?
I'm still listening. Can you put up the presentation? I'm listening. I'm using my mobile now.
Oh, let me give you power to share so you can share your screen. If it doesn't share, then I'll share from you. I'm sure from my end. Would that be okay?
Just go ahead and share until I have my system up and running.
Okay. I understand. So we are here. Just continue from here.
Okay, fine. That's good. So I was talking about the method of heat transfer, and there are actually 3 methods of heat transfer. And the first one, can everyone hear me? I hope I'm audible enough. Uche, confirm, please.
Yes. Yeah, you are. Go ahead.
Okay, very well. So we have the first one, which is heat conduction. Now, heat transfer by molecular contact, and it's mostly effectively in solid materials. Okay, now this is heat transfer when solid materials are in contact to themselves. So when one atom gets heated up, it impacts the next atom, and then it keeps on impacting on the next atom, and that is how the heat is keep being transferred. That's why when you hold a spoon and you dip it inside a hot water, the part of the spoon that is immersed inside the hot water absorbs the heat from the hot water, and then the molecular transfer of the heat begins to occur on that metal spoon when it gets to your hand. Okay, so that is conduction. Then you have convection. Now, this is the heat through density difference, most effective in liquid and gases. Now, the example I just cited now, where you dip a spoon inside a hot water. Okay. Now, you can imagine that the part of the water that you dip the spoon is not hot, but you just added a hot water from the other end of it. Now, the process of that heat in the hot water that you just added, moving towards the point where you have that spoon, is known as convection. So it's also a molecular movement of liquid and all of that. They have the thermal radiations. This is heat transferred by wave motions. There is no material required. This can occur in space. This is how the heat energy from the sun reaches the earth. Okay, so these are the 3 basic mode of or method of heat transfer: conduction, convection, and radiation. Please, can you move to the next slide, Ishe?
Okay.
Okay, now, just like what I've explained now, okay, that is the mode of heat transfer. Then you have types of heat. There are 2 kinds of heat. So you have the sensible heat. Okay, so we can sense it by touching the substance directly or indirectly with a thermometer. So when I talked about spoon, when you dip a spoon inside the hot water and the spoon gets heated up, that is a sensible heat. Okay, you can feel it. Okay, by touch you can feel it, or even just getting your body close to the object, you can also feel it. So those are sensible heat. If 2 different objects have 2 different temperatures, and you touch the one with lower temperature, you feel that it is hot but not very hot. If you touch the one with a higher temperature, you also feel that it is hot and it is very hot. So those are sensible heat. But there are heats that you cannot feel. Okay, and those are what we call latent heat. Okay, now this kind of heat are the energy needed to change a substance to a different form. Okay, so example is changing water from liquid to water vapor, or changing water from liquid to gas. Okay, if you're heating a water from 0 degrees centigrade until you get to 100 degrees centigrade, and you keep applying heat, the water will no longer absorb. I mean, the water will absorb the heat, but what it's going to do with that heat energy is to transform, to change phase, to change from liquid to gas. That's what it. So if you look at the picture beside it, you see a kettle that is boiling. So that is latent heat. Okay. I think we should go to the next slide. There's a slide that depicts this exactly. So now this is now being illustrated using water. Okay, water changes phase at different temperatures. When you extract heat from water below the 0 degrees centigrade, so this is a typical example of what happens in your fridge or your freezer. Your freezer just extracts the heat from the water or from the food that you've stored in it, And when it gets to 0 degrees centigrade, it begins to solidify. It changes phase from liquid to solid. When it is in solid state, you bring the food out, you begin to add heat to it. When it gets to 0 degrees centigrade, before it enters +1, it begins to change phase. Between between 0 and +1, it begins to change phase from solid to liquid. And if you keep applying heat to that water or to that food or whatever it is, if it gets to the boiling point, for water, the boiling point is 100 degrees centigrade. If you keep adding that heat, you're not going to achieve any temperature increase. Rather, you're going to achieve a phase change. So the water will change from liquid to gas. Okay, so that is what we call latent heat. So from 0 degrees centigrade to 100 degrees centigrade, you have sensible heat. Then from someone just type something.
Go ahead. Maybe later you just reply. Go ahead. I will take.
No, we are not seeing the temperatures, 0, minus, and the ones you are mentioning on the graph.
Okay. Chima, did you understand the question? Hello, Chima. Okay. Okay.
The temperature.
Hello.
Please.
Yeah, understand. Okay, let's look at it here. You can see my slide. I think we lost Chima again. Let me also remind us once again that I wanted to tell Chima to take it faster because it seems we are a little bit slow, even though it's important that we lay this foundation so that when we go into the more complex things, we'll not find anybody wanting. Now, this is the ice phase. So this is the melting point. So here is 0, point B. So point A is below 0. Okay, point B is 0, of course. And then between point 0 and 4, this is point C is 4 degrees, if you remember. So between 0, B, and C is this complex phase, okay, where you have this change in phase. They call it the ice-water mixture. Then from C here, the liquid becomes fully water. So between 0 and 4 degrees, is a little bit ice-water mixture. Then from C until it gets to point D, that is when you have 100 degrees, which is the boiling point. So from what Chima is saying, if you keep adding temperature at that point, if you keep adding heat or applying energy, there won't be any change of phase until you get to the saturated vapor pressure, and then the water will start to go into superheated steam. So let's say that 100 here is 0, is 100, is D is 100. Then between D and E is the water steam mixture, which is a function of the fluid, okay, based on the viscosity and the density, and that will determine the next phase. And then after then, it goes to point E, where you now see it becoming like a superheated steam. So I don't know if that suffices. Okay, Chima.
Okay. Thank you very much, Engineer Uche.
Once you come back, just let me know. I'll pause.
Okay. So I don't know if this is clear, and the reason why I decided to emphasize a little more on this is because when we now go into the energy efficiency in the industries, we will now begin to talk about boilers. If you understand this concept, it becomes easy for you to understand how the boiler system works, because the boiler system is all about the production of steam for industrial purposes. Okay, so this is more like a foundation, and you need to understand all of this. That's why I'm taking time to explain it. I can move a little bit faster, but I just don't want to rush it without passing the knowledge. Okay, so thank you, Engineer Uche, for coming in there. So can you move to the next stage? If anyone still have questions, you can please do wait to ask. Otherwise, let's move to the next stage. Okay, so this is utilization of energy. Okay, next please. So I want to explain the processes of energy transfer and how the inefficiencies come into all of this process. Okay. if you can think back from the point where you have your primary fuel, so at the time where you have your coal, from this image that we are seeing now, from the time you have your coal, you have your 100% energy as in the form of coal, but it goes into the thermal power plant, in the production of electricity, coal power plant, with the purpose of converting that coal to electricity, okay? So by the time you're having your electricity, you have lost almost 70% of the energy it contains as coal. So you're left with about 30. So, and this process continues up to the point you have transmission losses, you have distribution losses now in the form of electricity, up to the point it gets to your house or to the factory. You now put that energy into your industrial application. So if you're using industrial motors, you now use that electricity to power your industrial motor. Those industrial motors have losses. Okay, so if you're using that industrial motor to pump, to turn a pumping machine, okay, there are also losses between the motor and your pumping machine. So the point is that before you get to the final end, where you actually need the water. So if you need that water to be pumped at a certain height, maybe you're on the 10th floor, you need that water to be pumped from the ground floor to the 10th floor. At the time that water is coming out on the 10th floor, the amount of energy that is remaining in that water will have been significantly been reduced. Okay, and how we relate this energy output from the initial energy that you started with is what we call the coefficient of efficiency. Okay, and that's what we have up there as a formula. So you have coefficient of efficiency, which is the useful energy, which is the energy that eventually come out at the 10th floor. The energy content in the water you have at the 10th floor, all over the energy you started with, the 100% energy you started with as coal. So that is simple definition of efficiency, coefficient of efficiency in this case. So if you take it a little bit further, you now have the energy input, that is the 100% that you started with, minus all the losses along the line, then divided by that same energy input, okay? So you have the coefficient of your energy efficiency. The next slide, please. Okay, so now this is talking about indicators, energy indicators. Energy indicators is simply a way for us to also measure how efficient our energy systems are, okay? So the first one you have there is the specific energy consumption. Now, this is very important energy indicator, and I will explain. If you're running an industrial processes, for example, you're producing a biscuit, okay? It is important you know the amount of energy you expend to produce 1 kilogram of your biscuit. So if, for example, you use 5 units of energy to produce 1 kilogram of biscuit, what that means that your specific energy consumption is 5 kilowatt hour, or 5 units for 1 kilogram of biscuits. So if you produce 2 kilograms, you already know you're going to spend 10 units of energy. That's what specific energy consumption is for a specific production purposes. Or if you're running a hotel business, you need to know the amount of energy you use to service 1 guest room. If somebody comes and pays for 1 room per night, you need to be able to determine the amount of electricity or energy in total that it costs you to sell that 1 unit, one room for the night. So that's what specific energy consumption is. So it's a factor that tells us how efficient, okay, your energy system is. So you can also use it to compare between yourself and your competitors. If you're producing 1 kilogram of biscuits with 5 units of energy, and I begin to implement measures to reduce my own energy consumption, and I'm doing 3 units of energy for 1 kilogram, I'm going to be far ahead of you in market competition. I can begin to price my market less because you are spending more for 1 kilogram when I'm also producing the same 1 kilogram with less energy. So it's an indicator for us to benchmark and measure energy consumption. Okay, it is very quite similar with the next one, which is energy intensity. Okay, but in this case, energy intensity is the quantity of energy required per unit output or activity. Now, this is on a broader scale. So you're talking about GDP. You know, when you talk about GDP, there are so many things that comes to make up your GDP intensity. So if you take this now to factory that I use as an example, maybe you're also producing, maybe you can be producing density cannot be tied to your revenue, not to the product. Okay, if you're tying it to the product, it becomes specific energy consumption. But if you're tying it to your revenue, because there are so many products that now comes to form that revenue, okay, it now becomes your energy intensity. Okay, so that's just the difference between the two of them. Okay. Now let's go to electrical energy. Please, as I proceed, if anyone has a question, please do wait to ask. So the next slide, please. So let us look at the basics of electricity. Okay. When we talk about electricity, we talk about voltage, you talk about amperage. Now I want us to look at these two things like this. Voltage is like the pressure. We have water flowing through a pipe. Okay. The pressure that you the pressure through which the water flows is synonymous to voltage. So if you put higher pressure, you have more flow of water. Okay, so that's what voltage is in terms of electricity this time around. But in this case, you're not pushing water, you're pushing electrons. Okay, so now current is synonymous to the water itself. Okay, in the example that I just gave, if you're putting a pressure on a pipe to push water through, that water itself that you're pushing is synonymous to the current. Okay, so voltage is the pressure, current is the water that you need. Just look at it from that perspective. I'm sure a lot of us already understand it. So electrical power is when voltage and current work together to do something useful, such as turn a motor or light a lamp. Okay. So I think I already defined what power is previously. So now power is measured in watts. Okay. Watt is equals to voltage times ampere. Now that ampere is the same thing as current. Okay. Now when I was talking about power in the first place, I define power as voltage times the amperage, and I said that is not the real power. So when you now multiply that voltage and amperage with the power factor, then you now have what we call the real power. Okay. So we'll get to that in a bit as well. So can we just move ahead to the next slide?
Yeah, Rita raised her hand. Maybe she has a question.
Okay, please.
Rita, please.
Go ahead.
Yes, thank you. I'm sorry to just take you back. When you mentioned energy intensity,
okay,
I wasn't so clear about that because, yes, it's the quantity of energy required per unit output of activity, e.g. GDP, so using less energy to achieve. Okay, I was thinking when you talk about energy intensity, because that's what actually drives your energy demand charge. Mm-hmm. So I was thinking when you talked about energy intensity, you were going to relate it to the amount of energy or power you consume at a certain period or a certain time. I don't know if you get.
Okay. I understand your question, and I think there's a little bit of mix.
Yeah, because that is why we can relate it to GDP. According to my understanding, I'm just saying it because when you talk about an economy that is industrially driven and an economy that is service driven, the industrial driven economy is going to consume more energy, right? Mm-hmm. So yes, because the energy intensity there seems to be higher. Mm-hmm. So I was thinking you were going to relate in that energy intensity to some form of consumption level.
Okay. So I clearly understand what you said, and I think there's a little mix up here. So what you're trying to explain can best be described as energy use index. Okay. Or energy use intensity.
Mm-hmm. Yeah.
Okay.
Yeah.
These are two different.
Yeah.
Okay. Yeah. If you're talking about energy use intensity, now let me make this clear. When you talk about energy indicators, you have to relate it with an output or an area that is being served. I mean, there has to be two variables to relate with. Okay. Now let me try to explain this further. When you are looking at the level of energy consumption of a building, so for example, you talked about an economy that is more industrialized, okay, and maybe the one that is less industrialized. The one that is more industrialized will use more energy because it will have higher energy intensity. Now, for the fact that they are more industrialized, that energy intensity you're talking about, you have to correlate it with either their GDP or the output of that economy. So what are you measuring the energy against? That's the question. We know that they consume more energy, yes, but what are you measuring it against? Are you measuring with their GDP? Are you measuring with their revenue? It is expected that because exactly, or the weather. If you want to now look at the weather, okay.
Of course, definitely, of course. What I said, of course. I mean, when you look at developed economies and undeveloped or developing economies, you will see that in terms of economic growth, they are better off. And we can also see that there is a correlation between their energy consumption and their economic growth. And that is why GDP comes in. That's what I'm trying to say.
Exactly.
So I was expecting you to align it to that your energy consumption being related to your economic growth. That is why the example or GDP is now used to measure that consumption. It's just saying that, yes, there is economic growth, but there is higher energy consumption.
Exactly. So
Chima, can I just come in a little bit? I think you and Rita are almost you're on the same page basically. I think it is in terms of units. Okay, energy intensity is more like the aggregation, and the use of GDP here, I suppose, is like a is synonymous to GDP. It's not like GDP is a measure of intensity, because when we talk about GDP of a country, for instance, it aggregates a lot of factors. So unlike maybe when we go further down the line, when you start explaining things about SUI, which is a specific user index, maybe that will throw more light on what she's saying. But at this point, I think we have to move forward because
thank you very much. Let me just say this is not exclusive. Yeah, there is also energy use index, okay, and there's also energy price index. All of these are indicators, but it's just that I have not included all of those here. Okay, so we have more forms of energy indicators. Okay, so for the purpose of this training, and like I said, you're talking about economic growth. Economic growth is also tied to GDP, and that's why obviously why GDP is also used there. Okay, to relate your energy consumption with your GDP or your GDP growth. And over time, the economists have tried to decouple this relationship. Let me also state that there. It's a normal thing that when your GDP is growing, your energy consumption should also be growing. But the economists have said, no, we have to decouple this. Your GDP can grow, but let your energy intensity, let your energy consumption not also grow to be able to overcome this fight against climate change. So there's this effort to decouple your energy intensity with your economic growth or GDP. So Rita, you're very much correct when you talked about GDP or economic growth and energy intensity. We are all saying the same thing here. Okay, let's proceed. Let me go back to the previous slide. I don't know if I'll finish. Okay, let's go forward. You can allow me to share my screen. I think so that I don't have to keep asking you to move this thing.
Okay, just go on. I'll share. I'll action it.
Okay. So basic electrical formulas. Now, from the basic physics, we have the Ohm's law, which is voltage is equal to current times resistance, and then we have voltage. I mean V voltage, I is current, and then resistance, and all of that. All these are formulas that we are already familiar with. Then we have the Ohm's law for power, which is power is equal to current times resistance, and then we have power in watts. Then let me say that in most cases, your resistance can be constant. So if you have electrical systems, electrical wire, and the resistance, and you have a certain resistance of that electrical wire, it can be constant. So if you increase your voltage across that wire, you also increase your current. across that wire. So let me go to the next slide.
You can share now.
Okay.
Yeah. Also, lay emphasis on the power factor. I think you were on there before the question came on board.
I'm still unable to share, but just continue. Let me.
No, you can share now because I've made you the host, and I think I can't even share again. I'm sure of that.
I'm still unable to, except if I have to log out from my phone, and I don't want us to delay for that time.
Okay. Click on my name and make me the host again, so that I can continue to share for you. I'm okay with that. Just go to my name and click and say make me host. I made you host so that I can share your screen, but unfortunately you can't share.
Okay. Just a moment. Let me get to that.
Okay. And also be on the lookout for those who are in the waiting room. I think I just have to admit some other people now. So once in a while you go to the good.
Can you go ahead now?
Yeah.
Okay.
Let me see. I don't know. Yeah.
Okay. So this is an example about the Ohm's law that I talked about. I think there are people in the waiting room. Okay. There are 2 people in the waiting room.
Admit them. Just click on admit.
Yeah. I've just done that.
Okay. Please, once in a while, just go there and admit it.
Yeah, that's fine.
Logging behind.
Okay. So there's a question here. A 230 volt, 100 watt rated incandescent bulb is operated at a constant voltage of 250 volts. Now, the approximate power consumption of the bulb is that. Then there's a solution just by the side here. And what we do, because okay, let us look at what we are given. First of all, we are given the rated voltage, we are given the operating voltage, and we're also given the power. And then we are not asked to calculate what the power would be if the voltage is now changed. Okay, so if we have to solve this, we have to use our Ohm's law. We don't know what the resistance of that incandescent light bulb is. We don't know what the resistance is. And if we don't know what the resistance is, it will be difficult for us to calculate the power. So using the Ohm's law that we have stated earlier, voltage is equal to current times resistance. And then the second equation, which is power, equals to current square times resistance. So we make current subject of the formula in the first equation. So we arrive at equation 3. They will substitute equation 3 into equation 2. Then once we do that, we're going to arrive at power is equal to V squared over resistance. So at this point, we know what our voltage is, our rated voltage, not the operated voltage, okay? Which is 230. So when we put the rated voltage at 230, we put the power there. We put the okay. So we put the voltage at 230 and we put the power at 100. So with that, we arrive at a resistance of 529 ohms. Sorry, I omitted the symbol here. That should be 529 ohms. Then using the equation 4 to calculate power when voltage is now 250. Now, first of all, we calculated what the resistance of that light bulb is. So with that resistance, we can now determine, okay, what will be the power consumption if you vary the voltage. So if you change the voltage to 250, then you can now input the values to calculate what your power would be. So your power will now be equals to the rated, the voltage that the lamp is being operated at this time, square of it all over the resistance, which we have arrived at 529, and then we have 118 watts. This might look a little bit complicated, but at your own spare time, just look at it. That's why I took my time to explain the steps there, so that on your own self-reading, you can be able to understand it. The next slide, please. Hello, Uche. Okay. So Now let us look at electrical systems. First of all, we have different kinds of electrical systems. So we have the single phase electrical system. And then this is the power system having only one sine wave. And the frequency of that sine wave is 50 or 60 hertz. Okay, in Nigeria, we use 50 hertz, not 60. America uses 60. Nigeria, we use 50 hertz. Okay, so it's country dependent. Like I said, Nigeria uses 50 hertz. So it's, if you look at the graph there, you have the voltage across the time. So the wavelength is being drawn across the time. Let's go to the next one, please. So now we have the three-phase electrical system. Okay. Bear in mind that when we're talking about electricity, we're talking about the movement of electrons in this case. So now this is a power system having three sine waves. Now the frequency of each of the sine waves is either, like I said earlier, of course we use 50 hertz, and then the three sine waves are separated in time with a phase angle of 120 degrees. If you look at the sign there, you have the yellow, the red, and the blue phase. So where they are all separated with at a phase angle of 120 degrees. The next one, please. So let us talk about power quality. Now, power quality is related to how well an electrical system is maintains a pure sinusoidal wavelength at rated voltage and frequency. Nigeria, we use 230 volts, and then we use 50 hertz as frequency. That's the standard in Nigeria. So the power quality for Nigeria is expected, if I take a measurement of any power system, whether at industry or at home, at commercial facility, what I'm going to be looking at is the level of the voltage and of course the frequency. If the frequency is lower than 50 hertz, then it's not optimal. If it's higher than 50 hertz, it is not also optimal. Now let me explain what this frequency means here. We maintain a frequency of 50. Anytime it goes less than 50, what that means is that there is more load. I mean, there's more electricity. There's more electricity in the system. No, rather, it's the other way around. There is more load than the electron that is being transported. I don't want to get anybody confused here. When the frequency is higher, we have frequency above 50 hertz. What that means is that you have more electricity than the load that is consuming it. So you need to add more load. When it is less than 50, it means that you have more load than electricity that is being supplied. Okay, so if you are conversant with the system in Nigeria, often you will have heard that we have system collapse. Okay, when a system collapse, what that simply means sometimes is that you have more load than electricity that is being supplied, and at a point the generators could no longer carry it. Generators will just go off. Okay, that is system collapse for you, and is a function of the frequency. So the grid, the operators of the grid use frequency to maintain the stability in the grid. We'll talk about that much later. Then power quality issues involves all momentary phenomena, including spikes and outages, as well as harmonics. We'll talk about that in a bit as well. Modern electronic equipment both causes and is affected by by the problem of power quality. Then power quality is becoming one of the most important issues in energy management today. If your power quality is not optimal, it can cause a lot of problems for you. So we'll talk about that in a bit as well. Can you go to the next slide, please? So harmonics, I made mention of harmonics the other time. So let's talk about harmonics now. Harmonics are distortions of the normal electrical current wavelength. Remember when I showed you the single sine wave and then the three-phase wave? Okay, so these are the normal electrical wave. Please go back. Okay, so can you click the next? Click next. Because I want those images to come up. Okay, next. Okay, that's fine. Thank you. So, in other words, harmonics are multiple of fundamental frequencies. The first one, look at the first image here. We have the undistorted periodic wave. This is a standard wavelength, wave of an electricity. Okay. So if you look at the second image, you will see the blue wave there. It's called third harmonic. Okay. So what that means is more like a repetition of the fundamental frequency. Okay, so if I read exactly what I have, in other words, harmonics are a multiple of the fundamental frequency. Instead of having one wave, you have multiple of it in a space of one fundamental frequency. Okay, so when you now combine that harmonic, that third harmonic, with the fundamental wave that you should have, you will now have you now have the third image that I have there. You now have the distorted periodic wave. Okay, so now this was the original wavelength that we have, electrical wave that we have, and it has undergone through harmonic transformation. Harmonic has affected it at this point, and this is now what we have as the electrical wave, and this is wrong. This can cause problem in an electrical system. So this is what we call harmonics. We call this in electrical the power system as we call them harmonic pollution. Please go to the next one. So harmonics are generated by solid state based equipment such as switching power supplies in PCs, personal computers, DC drives, variable frequency drives, electronic ballast, arc welders, battery chargers, and UPS, and more. Okay, all of these are what actually induces harmonic into the electrical system. Next, please. Okay, most power systems can accommodate a certain level of harmonics, of harmonic current, but we experience problem when harmonic becomes a significant component of the overall load. So you have the first harmonic, you have the second harmonic, you have the third harmonic, fifth, sixth, and all of that. When the harmonic keeps coming, at a point, the electrical systems will begin to malfunction, and then you have a very poor power quality at that time. Remember, we're still talking about power quality. So at this higher frequency harmonics, as this higher frequency harmonics current flow through the power system, they cause communication errors. Like I said, you have the first, second, third, fourth, fifth, and then just like that. Then it can also cause overheating in hardware, and then of course overheating will cause hardware damage. It can cause metering error. Next. So all of this put together affects the power quality of a system. So like I mentioned earlier, we have what we call total harmonic distortion. So this is a measure of the power quality. Hello? It looks like I'm hearing myself. Uche?
We're hearing you.
Okay.
We're hearing you fine.
Okay. So the total harmonic distortion is a measure of the power quality as it's been affected by harmonics. Okay. So now what's the cure? How do you treat this problem in a power system? So we use harmonic filters. It's more like you're trying to eliminate all of those harmonic waves, so that it doesn't distort the fundamental waves. So they are called harmonic filters, and that's how you correct them in a power system. There are equipment that actually does that. For power systems. Please move to the next one. You're moving too fast. Go back, please. One more step back, just to be sure I've not skipped. Okay, front, forward. Just want to be sure I've not skipped any slide. Okay, so now we need to talk about voltage after we've talked about harmonic. So problems can occur because of voltage imbalance between the three phases. Uche, please go back. Are you sure I've not skipped something? Okay, it's fine. It's okay, just hold on, it's fine. Okay. So problems can occur because of voltage imbalance between three phases. Now, voltage imbalance is basically a problem of three-phase system, not single phase. Okay, so this can be a serious problem in motors. It really affects the operations of motor systems. So percentage voltage imbalance is found as the ratio of the largest phase to phase voltage differences from average. Now, divide, I beg your pardon. Percentage voltage imbalance is found as the ratio of the largest phase to phase voltage difference from the average. Now you have to divide by the average voltage. Now what this simply means that if you have a three-phase system, for example, you have 220 volts, you have 215 volts, you have 210 volts. Now this is a three-phase system, right? They are all operating at different voltages, 220, 215, 210. And mind you that this is powering one equipment, perhaps a three-phase motor, okay? Now, because they are not all on the same voltage, there's an imbalance between them. So we need, how do we calculate the level of imbalance between these three voltages? That's what voltage imbalance is all about. And this is, I'm going to explain how we can calculate that. So first of all, you need to determine the average voltage of the three phases. So you need to determine the average between 220, 215, and then 210. Okay, so when you add all of them and divide by 3, you have an average voltage, which is 215. That is average. Now, the voltage difference are, for the first one, you have 5, which is 220 minus 215. You have 5. The second line, you have 0. 250 minus 215, you have 0. Now, the third line, you have minus 5. Okay, which is 210 minus 250, you have minus 5. Now, positive or negative is not relevant because it is alternating. You remember we were talking about alternating current here and all of that. So the voltage imbalance here now is the highest difference, okay, which is 5 in our case, divided by the average voltage, which is 215. So when you do that division, you're going to have 0.023 or 2.3%. That's when you divide the 0.023 by 100, you have 2.3%. Are we clear on this? Do you have any questions? Okay, the next slide, please. So let's have further example on that, okay? So if we have 400, 385, 409, now this is a three-phase board, okay? Now the voltage imbalance is dash. Now the maximum deviation from the average divided by the average voltage. Remember, this is the definition of how you determine the voltage imbalance. The maximum deviation from the average, you divide it by the average voltage. So the maximum deviation we have there is 13. Okay, so click the next slide. Just click next. I think this. Okay, go back. I thought I had put further explanation to that. So no, go back. Okay, so the maximum deviation from the average is 13. And how do we arrive at 13? We determine the average of the three voltages, which is 398. Okay, when you now subtract them from the three voltages of the three lines, 400, 385, and 409, the highest difference you're going to have is 13. So when you divide that 13 by 398, you're definitely going to have 0.033. When you divide that by 100 to convert to percentage, you have 3.3. So the voltage imbalance is 3.3%. Okay. So if the lower the voltage imbalance, the better. The higher the voltage imbalance, the more problem you have for the system, and the more you have a poor power quality. Okay. So next slide, please. So this is further example of the imbalance in three-phase systems. Now, this you can at your own time you can go through this. You have the yellow, you have the red, you have the yellow and blue phase. Then you have the average value. That is average volt for the across the tree. Then when you now do the division, you have your imbalance in percentage there. So there are about 4 of them. Next one, please. This is further examples for you to solve at your own time. Let's proceed. So what are the problems of imbalance phases. We have imbalance phases. Okay, so let's look at overvoltage. When you have your imbalance phases on the high side, we have overvoltage across your lines. What are the problems that could happen? One of them, you have electrical equipment overheating. Okay. Then the next one is that you have electrical circuit failure. You can have your electrical system tripping because of the overvoltage. Then you have reduced equipment operational life. Then you have production and operation impact. It can also impact your production processes and all of that. It might even get to a certain point when your equipment might refuse to function or they begin to function abnormally. So these are the problems of overvoltage. The next one, we're going to see the effect of undervoltage. Next, please. Okay, so these are the problems that occur when you have an undervoltage in your system. So you have lack of sufficient power to operate your electrical equipment. Okay. Then you have electrical system also overheating. They have reduced motor torque. Torque is just the rotational speed of your motor and all of that. So you have reduced torque on the force that actually rotates your motor. You have reduced motor torque. They have motors overheating. They have reduced equipment operating life. Then you have also production and operation impact on your system. Next, please. So let's look at power factor. Let's proceed.
Sorry, a quick question.
Okay.
At what value of the deviation signals a red flag?
From your I mean, you're talking about imbalance in your voltage,
yes,
right?
imbalance. What value do we think we should now start to become concerned?
It actually depends. I mean, the ideal thing is to actually bring it to a balance, okay? But when a certain line begins to fall out of, maybe the voltage begins to increase, then you begin to have problems. So the ideal thing is to bring them, to a balance. But if you ask me, I think it shouldn't go above 20%. I mean, 20% is even high.
Okay.
Yeah, it's high. 20% is high, but you shouldn't. Now I'm saying this based on I'm saying it based on the my knowledge on frequency. Okay? It's not like there's a standard that I'm trying to put here, but I'm saying this based on my knowledge of frequency. For the frequency, if you go beyond 25, I think that's the point where you have a system collapse in Nigeria. I mean, 25%. That's when you have a system collapse in Nigeria. Not 25%, 2.5%.
Wow.
Yeah, 2.5%. Sorry, not 25. Yes, if you go above 2.5%, you're going to have a system collapse. If you go below 2.5%, that is minus 2.5% in this frequency level, you're also going to have a system collapse. Okay. Yeah.
Anyway, Nigerian system is very obsolete, so we expect that to happen.
Exactly. We usually have that almost all the time. So for the voltage that you asked, I can't give you any state because I don't have any standard to reference now to say, okay, this is the tolerance level that you should go, right?
Okay.
Okay.
All right, thanks.
Next. Okay. So we are now talking about power factor. So power factor indicates how well the current and voltage are working together. Okay. A number from 0 to 1 or 0 to 100% if you're doing a percentage and all of that. Okay. And then it is being represented as the real power over apparent power. Earlier in the I made mention of real power and apparent power, and the only difference here is what only makes the difference here is your power factor. Okay. So in this very section, we'll dive more into the detail. Okay. So now the ratio of how much of the power supplied, how much of the power that is supplied that can be used to perform useful work. Okay. Not all the power that comes into your facility that are being used to perform a useful work. So the ratio that is used to actually do a useful work to the one that's actually coming to the facility is what we now call your power factor. Okay. So power factor is dependent on the load. in the electrical system. Okay, so as we proceed, we'll look at different kinds of load in the electrical system. We'll look at the load that actually induces power factor problem. So power factor reduces the amount of useful power. So the electricity that comes into your facility, when it gets to the load that actually consumes that load, the load has effect on the quality of that electricity. And that's where power factor plays, okay? That's where power factor is being affected. So I made mention of apparent power, which is kVA. The actual power that comes into your house is in kVA. When it gets to the point of your consumption, it's now transformed into kW, which is the active power next to it, you know? Yeah. So if someone has a question. Okay, someone is asking, how can you correct voltage imbalance? Okay, you might need to begin to adjust your load. So sometimes the reason why you have voltage imbalance is because you have higher amount of load on a particular line. Okay, so we have a higher amount of load on a particular line. It's going to actually draw, it's actually going to drop the voltage on that very line. So if you have 10 lines in a building, I have 8 lines connected to yellow phase. Okay, it is expected that you're going to have a lower voltage on that yellow phase, okay, than the blue and red phase. So you need to balance your load. You need to take out some of the load and then balance it. That's how you do. That's how you balance your correct load. Someone is saying. Someone raised his hand. Any raised his hand, and please, if you're not speaking, mute your mic. Okay. So
you were talking about the frequency limits, the accepted and nominal frequency. I think I can help with that. I said I can help you with that.
Okay.
We were concerning frequency and the voltage. The nominal frequency is 50 Hertz in an ideal situation, but in life, there's no ideal. The National Control Center, which is under Transmission Company of Nigeria, they come in with that, and then NEC and all that. So we have the Greek code on frequency and voltage as well. So what is permissible is plus minus 0.5%. So that will give us a range of about 49.75 Hertz to 50.25 Hertz. And then under abnormality, we can also maintain 50 plus minus 2.5%. That will give us like 48.75 to 51.25 is acceptable.
Okay.
Then we were talking of voltage balance to correct voltages. Yes, fine. When we have excessive voltages, what do? When there's excessive voltage and all that, it shows that we are not taking enough load. When we have excessive voltage, we have what we call, we have like at the transformer end, we have what we call tap changing.
Okay.
And then when you have excessive voltage as well, it points that you are not taking enough load. So you introduce what you call your inductive load. For us at home, your borehole is an inductive load. So at the transmission stations, they have what they call reactors. Reactors are inductive load. So when the voltage becomes too excessive. Hello, sir.
Yeah, I'm with you. And I'm coming to that, okay? Let's not move. I'm coming to that. I'm coming to resistive load, inductive load, and capacitors and all of that. But that speaks more to your power factor, right? I understand what you've just said is not different from what I said about the frequency, that we have a tolerance level of 2.5, to which at the point, if it exceeds that level, then the grid can collapse. There is 0.5 limit, which yes, but the maximum tolerance limit is 2.5. right? Which is the same thing that you've just said. I totally agree with you, and we are saying the same thing here. Then for the voltage that you talked about, when there is excess voltage in the system, yes, it also means that you're not picking up more load than you should. But in this case, we are also looking at the imbalance between three phases. If you overload a single phase and underload the other phase, the load that the phase that is being overloaded, it is expected that the voltage will be lower than, because there's more load to it. Just like you said, if there is excess voltage, it means that you're not picking load. Okay, so what you've said is valid, and I clearly understand that, and I hope it also helps other learners, other participants, to get a clear view of the issue at hand.
Thank you, Ene. That was good.
Yes, very well. Okay, so thank you very much for that. So back to the apparent power and then the active power. Okay, so I said that what comes into your house is actually the apparent power. When it gets to your load, where it is being consumed, it's now being converted to an active power, which is kW. Then you have also reactive power, that comes along, which are more like the wasted electricity. So let's go to the next slide, please. So Anna was talking about some types of load. Okay, so this is I think this is what she was trying to describe. Okay, so you have a resistive load. In an electrical system, volts and current both ideally have a sinusoidal waveform. If the current and voltage waveforms are aligned and they reach their maximum amplitude at the same time, then the current is said to be in phase with the voltage, and no kVAR. kVAR is reactive load. Okay, so there is no kVAR present at that, which means there is no wastage of electricity at that point. Okay, so example of such load are your heaters, your electric heaters. They convert 100% of electricity that comes to them into heat. There's no wastage. It's 100%. We usually say there is no 100% efficiency, but this is actually proving it's wrong, ironically. So 100% of electricity that comes to your heaters are converted to heat. No waste. Your heater, your geysers, your incandescent lamp bulb, and all of that. So your incandescent lamp bulb, this is the reason why it is being phased out. It's more of a heating load, okay, than lighting load. Okay, almost 95% of the electricity that comes to is converted to heat. Then about 5% is converted to lumens. Okay, so it's a lot of waste in the system. Okay, so if you look at that, the diagram by the side here, you will find out that the voltage and the current they're almost achieving their maximum amplitude at the same time. There's no change, there's no difference in their phase here. So whenever I see this kind of wave, it aligns perfectly, and your power factor is unity. It is 100%. And the kind of load that can give you this kind of systems are maybe water heaters and all of that, resistive load. Okay, so let's move to the next one. Okay, so now we have inductive load. Now this is where the problem is. Okay, however, if the system voltage reaches its maximum amplitude before the current, then the reactive power, this kVAR, are said to be lagging. Okay, if you look at the next figure there, you find out that the voltage reached the maximum amplitude first before the current. Okay, so there's a shift, in that system now. So when you have something like this, then your kVAR is not induced, which is a wasted electricity is not induced in the system. An example of such load are motors, transformers, and loads with coils. Okay, so all of this load that has coil actually induces the kVAR into your system. Okay, and it displaces your current and voltage, put them out of phase, and it wastes electricity. So the magnetic field in this causes the current to slow down, and then you cannot have a power factor that is 100%. Your power factor will always be less than 100%. So these are inductive load. Your motor systems, your transformers and all of that are inductive load, and they affect your power factor. The next, please. So we now have the capacitive load, okay? Now I've talked about resistive, I've talked about inductive, now this is capacitive load. Now on the other hand, if the current reaches the maximum amplitude before the voltage, you know, in the inductive load, it was the voltage that reached the amplitude before the current. Now, the current is the one who is now reaching the amplitude before the voltage. So it's more like the opposite of the inductive load, right? And this is how you correct power factors, okay? You have to induce capacitors. So example of such capacitive loads are capacitors. Now this load increases power factor. Your inductive load reduces power factor. Capacitors increases your power factor. So you use capacitors to improve your power factor. Okay, so that is the three basic kinds of load you have in the electrical system. The next, please. So now this is an analogy of a beer, trying to describe the three kinds of power that we have, okay? So we have the reactive power, which is the foam. And you know, when I keep talking about wasted electricity, that's the kVAR. That is what I'm talking about, okay? What actually comes into your house is the kVA. The real power, which is the real beer plus that foam, is what actually comes into your house. But what your appliances actually use is the real power, which is the beer. Okay. If you have motors, equipment in your house, they will begin to foam. They will create that foam and they will form wasted electricity. It becomes a problem. Okay. So the way to represent this is using this beer analogy, and they're using a triangle. Okay. It becomes easier to do all the calculations and all of that. And the angle, the displacement angle between the voltage and the current is what we know as cos pi. Okay, if you look at that triangle, you see. Hello?
We can hear you, Chima. We can hear you.
Okay. So the cos pi there is actually the displacement angle between the voltage and the current that actually induces the kVAR. So if that cos pi is 0, what means that kVAR will not exist. That blue arrow will just lie flat. Okay, and that's what actually happen when you have resistive load. Next, please.
Yeah, Chima, let me also remind them that from what you said, we are paying for kVA. So
exactly,
there's a waste in what you are paying based on the kind of equipment you are using it to power. Thank you.
Yeah.
That's a good analogy.
So thank you very much, Engineer Oche. Okay, so now power factor formula. Okay. I talk about apparent power, which is actually the one that actually comes into your house. Like it is VA, voltage times current. Okay, if you now divide by 1,000, you have kVA. But in this case, we are leaving it as basic as it is, VA. Okay. Now, for us to do all the calculation around the three different kinds of power that you use, the apparent power, the reactive power, and the real power, to help us solve this mathematical problem, we have to go back to our Pythagoras theorem. I will also have to make SOHCAHTOA our friend. Okay, I don't know how many of us that still remember SOHCAHTOA. Okay, so if you understand the Pythagoras theorem and the SOHCAHTOA, you can solve any problem around power factor. If you're able to draw this triangle, you can solve any problem around power factor that exists, whether in certified energy auditor or as a certified energy auditor or as a certified energy manager. Okay, so the true power here is the actual, that is the W or kW, is the actual power that you use to power your appliances, your fridge, your light, and all of that. Okay, that is the true power. And how do you determine your true power? Your true power is your VA, that's the apparent power, cos theta. Okay. How did we come about this? You want to create a relationship between real power and apparent power. Okay, that is, now your real power is adjacent, sorry to say. Your real power is adjacent. Now I'm trying to relate this triangle to the SOHCAHTOA. Okay. Your reactive power is opposite. Then your apparent power is hypotenuse, right? So if you want to relate apparent power with real power, okay, you look at the SOHCAHTOA. What correlates hypotenuse and adjacent?
Sine.
Okay. Sorry?
Sine with sine.
Exactly. Okay. Is that?
Opposite and hypotenuse.
Opposite and hypotenuse is sine. Exactly.
Yes.
Okay. So what I'm trying to what that speaks to reactive power actually. Okay. You're talking like the sine, the sine relates the apparent power and the
reactive power.
Okay.
And the reactive power. No, it's cosine.
No.
Cosine is okay. Adjacent to hypotenuse. Adjacent to hypotenuse is the real power, which is
exactly. Which is the true power, so, which is the W.
Yeah, which is cosine. SOHCAH.
Exactly. Yeah. So the point I'm trying to establish is to make us understand how we arrive at the formula for the true power and the reactive power. The apparent power is always fundamental. Voltage and current is always fundamental. Then based on that, you can now determine what are your true power and then your reactive power. Okay. So the primary Pythagoras theory, which is the hypotenuse square all over adjacent square plus opposite square. That's what we have VA square plus W square plus VAR square. This is all of these things are just Pythagoras theorem. Okay, so let's proceed. When we begin to solve examples, it becomes very clear.
Yeah.
Next, please. Okay, so example: if true power is 700 watts and cos pi is 45.6 degree. Now, if you punch your calculator, if you do cos 45.6, what you're going to get is 0.7, which is your power factor. Maybe I don't know if I mentioned that your cos pi is the same thing as your power factor.
Yeah.
Which please go back to that triangle. Yes, exactly. So this your theta here. This theta that you're seeing, the angle of displacement that you're seeing there is actually your power factor. Okay. So it depends on what you're relating it with, either with cos or with tan or with sine. So cos theta, sine theta, or tan theta will give you your real power factor. So let's go ahead. So in this example now, we are giving power at 700 watts. Our power factor is 0.7, which is the same as cos theta at 45.6 degrees. Then what is the apparent power, which is VA? So solution, if you take the formula that we have from the other slide, then you have true power, which is equals to VA times cos theta. Okay. Your V is your VA's power is already given as a sorry. So in this case, we need to calculate our apparent power. We are giving true power and we are giving cos theta. I would have made it easier if I had drawn that triangle. It would have been easier for us to understand. But I know in the next example, I drew that triangle for the I know. It's okay, just leave it like this. Yeah. So your true power is VA times cos theta. We know what our cos theta is, which is 0.7. Okay. But we don't know what our VA is. That's what we're looking for. And we are giving true power. So from that first equation, we make VA subject of the formula, and that will give us the true power all over cos theta. Okay, so cos theta is 0.7. So 700 watts over 0.7 will give us 1000 VA, and that gives us the answer. Okay, the next slide, please.
So Chima, it means if I am buying a generator and I'm using an inductive load, and is having like the power rating is 700, it means I should be going for a generator that is rated 1000 or 1 kVA. Am I right?
Exactly.
Good.
Yeah,
so
that's
I want them to understand it that way. So it means if I'm going to the market now for me to power my inductive equipment, motor or whatever that has coil, it means I'm not going to buy a generator of 700 watts. Rather, I'll go for an apparent rated machine generator of 1 kVA.
In terms of the kVA of
VA. Because that's how they rate generators in the market, I would say.
Exactly.
That's a good one.
So,
okay.
So when you hear the ratings of generator, you can see 1000 kVA. Okay. Now that 1000 kVA is the apparent power. It's not the true power that it can deliver. So unless you're using that 1000 kVA to power a resistive load, your power factor is 0. But if you're not powering a resistive load, you have to consider your power factor, which induces waste in it.
Yes.
Okay. So that's what it means. Thank you very much, Engineer.
The 300 there is not like the bubble in the beer. Okay.
Yeah. So now this just putting everything together. This is power factor correction. Remember, I talked about the resistive load where you don't have any waste. You have the inductive load where you have motors that actually creates the waste. Then you correct it using capacitor. So I've discussed this. So let's move ahead, please. So now we'll have to look at kVA. That is, how do you correct that waste? Okay, the kVAR, in your system. So in trying to correct that, remember I talked about capacitors. Okay, you have to, if you have a power factor that is less than 100, you need capacitive load to drag it up. Okay, so how do you now determine the size of the capacitor that you need? That's how we correct power factor problem. And that's what this section is going to talk about. How do you determine the size of capacitor that you have to put to correct your power factor? Okay. Now, in correcting your power factor, okay, you need to multiply your real load, your real power, that is the kilowatt or the watts, times a table factor. There's a table factor I'm going to show to you. So from that table factor, we pick now this is a computational algorithm that has already been created by experts. So you just look at your current power factor and the power factor that you want to achieve. So, let's go to the next table so I can just demonstrate. I can show that. Okay, fine and good. This is a table factor. This is a power factor for correction of kVAR. kVAR is a waste, that causes poor power factor. So if you look at the top, you see desired power factor. The second line, you see desired power factor. When you look at the next row on there, you see different values of power factor. Okay, so you have to look at the value of power factor that you desire. Then on the left, on the first column, you will see original power factor. So if you have an inductive load in your house and it's affecting your power factor to be poor, maybe, so for example, if you have power factor of 0.7, okay, and you want to correct it to 100%, 100, then you have to trace that 0.7 across up to the point where you have 100%. So you see 1.02 there. So that becomes your power. That becomes your table factor. Yeah, that becomes your table factor to improve that 0.7 to 100. If you want to improve it to, so for example, you want to improve to 0.9, you have to trace 0.7 till you meet 0.9. No, you pass. You should go back. Exactly. So you have 0.536. It becomes your table factor. Okay. So that's how you use this table factor. Let's go down to the next slide. There's an example to explain this. So this is a sample question. A facility is operating at a power factor of 70% or 0.7. What with a real power load of 2000 kilowatts? So you know the true load, 2000 kilowatt. You know the power factor 70% or 0.7. How much corrective capacitance in kVAR is needed to improve the facility power factor to 90% or 0.9? Okay, so there are options here. Let's go down to the next slide. So we'll solve this together. So if you remember, we have a power factor of 0.7, and we desire it to be 0.9. So is zero, okay, yeah, which is okay, just keep it at this. So you have 0.7 and you want a power factor of 0.9. If you look at the coincidence where 0.7 meets 0.9, you finally have 0.536. So that becomes your table factor, okay? All you need to do is to take this table factor and multiply it with your true power, which was given at, next slide, please. Yeah, so just take it and multiply with your true power, which was given at, what do we have as 2000 watts? Okay. Go to this, go to the solution. Yeah, exactly. So now, this is what we have at present before we begin to do our correction. You have 2000, look, I'm looking at this triangle now, look at that triangle. You have 2000 watts as your true load, right? We don't care about the kVA. What we care about is the kVAR, because we want to reduce that inductance, that's wastage there. We want to bring down that triangle to 90. So it currently is at 70. We want to reduce it to 90, okay? So we have checked our table factor, and what we find our table factor to be is 0.536, okay? If you multiply that 0.536 to the true power, which is 2000 kilowatts, you will arrive at 1072 kVA. So that is the capacitance that you need to improve power factor from 0.7 to 0.9 or 70%. You should click the next one you see after we've corrected it. Exactly. So what we have initially was kVA1, which was 0.7. Okay. Now we've been able to improve it from kVA1 to kVA2, which is now 0.9 or 90%. So you see that we are reducing that wasting, we are reducing that kVA. If it eventually hits 0, then we will have 100%. Okay, but at this point, what we needed was to reduce to 90%. And we are trying to determine the size of the capacitor that we need to do that. So the size of the capacitor we need to do that is 1072 kVAR, kVAR. Okay, so that's what we require. So let's move to the next example, please. So a facility has a 100 watt electric resistance oven for drying, for drying parts. What is the power factor of the oven? I mean, can anyone answer this question? A facility has a 100 watt, don't click next, please. Just hold on.
Let them type it.
Yeah,
let them type it.
Yeah.
On the chat box.
You have the option there. You have D 100% from John. Okay.
Don't mention. Let them let them mention. Let them solve it. I think tomorrow the class might be more, when we start the calculation, it might be more interactive. So get ready. As Chima was saying earlier on, get your calculator standby. It's going to be more interactive and we'll be solving questions.
Okay. So I think a couple of them has presented the answer, and all the answers that I see are saying 100%. And I think you all are correct, because this is a resistive load, okay? There is no wastage here. Power factor is 100. Thank you very much. Let's proceed, Michelle.
Okay.
Okay. So now the next question is, a facility has a motor that draws 200 kVA and has a power factor of 70.7. How many kilowatt, that is the true power now, and how many kVAR does it draw? Okay. The kVAR is the waste. You want to know what is the waste, what is the true value. We know what the power that comes into the facility is, which is the apparent power, kVA, which is what you're paying for. But you want to know how much you actually use, which is the kilowatt, and then how much that was actually wasted, the kVAR. That's what this question is asking us. Okay, and there are options here. So let us look at the solution without wasting much time. First of all, we draw the triangle. You can see that what is coming into your facility is 200. Okay. And you know your power factor, which is 70.7. Okay, so first of all, we are given the power factor. 70.7 is 0.707. Okay, And then, yeah, of course. We should click the next so that the next slide comes out. Okay, fine. So from 0 point, given for the fact that we are given the power factor of 0.07, we are not giving this as, so we don't know the angle of displacement, right? We are just giving the power factor, okay? So how do we now find the angle of displacement? All we need to do is to do anti-cos, okay? If you do an anti-cos of 0.707, you get the angle, which is 45 degrees. Okay, if you have calculator, you can just do that anti-cos 0.707, you get the angle. We need to know what the angle is, the angle of displacement, to be able to calculate the wastage and the actual power that we use. So having established the angle to be 45 degrees, 45 degrees, not centigrade, please. So we now look at our the relationship between true power and apparent power. Remember that your true power is your, if someone has posted an answer, your true power, that's very good if you've been fast enough to solve it. I hope it's correct. Okay, so your true power is your apparent power times your power factor. Okay, so we've established what the true power is, 141.45 kilowatt. So then what is our kVAR? Which is, go ahead, click on. Yeah. Okay, so we have to look for kVAR. kVAR is equal to the apparent power sine theta. We know what the sine theta, we know what the theta is, which is 45. Okay, so we now have the 200 times sine theta is 0.707 at well. So we'll do that. We'll also arrive at 141.42. Okay, so what option do we have there as the right answer? C. Okay, correct. The person that posted C also actually got it correct. So thank you very much. Let's proceed to the next example, please. You have access to this material, so you can, on your own, you can go through it and then study. Okay. So now the third question is, a facility has a motor that draws 200 kVA. And before I proceed, I just want to let you know that all these questions are extracted from the actual Certified Energy Auditors exam. Okay, so we are not just putting it because we decided that we want to teach you. These are questions from Certified Energy Auditors exam that we extracted, and we are presenting them here. Okay, so a facility has a motor that draws 200 kVA and has a power factor of 80% or 0.8. How many kW, that is the true power, and how many kVAR does it draw? This is similar to the previous question that we did. So don't click the solution. Let me allow them to solve this, maybe about 10 seconds to solve it, and then see how many people are going to get it right.
You say 10 seconds or 1 minute?
If you say 1 minute, they will take 2 minutes.
Okay. So, gentlemen, let's just put a hand on it. The materials has been shared on our chat box, but let me quickly share it again. Tim, I don't know. Let me share it again. Why they are solving it anyway, for those who might not have it.
Okay.
Let me share it again. Let me share it again so they can have it on their system also.
Have you clicked the answers already? I thought they're solving it.
No, I have not. Did I?
You have.
Oh, the answer is already please don't look at my screen. Don't look at my screen. Don't look at my screen. Let's behave mature, please.
No, but I finished solving it, so
let's be mature. Understanding energy and little basics. So I've uploaded for those who came late. My apology for those who came late. About 7 people came late. I was trying to, I was not in charge then. And one take home I want to take from what Chima said is that most of every exercise and example you've seen in the course of this training are actually extracted from the internationally recognized Certified Energy Auditor, which is something that is growing in Nigeria. And that's why this training is coming up. So the end game for this training is not just for you to attend the training, is to explore how you could get certified in the future when you are ready anyway. And that could be in 6 months' time, in a year time, or when there's need for it. So let's have that at the back of our mind, that this training is a long-term vision, it's a long-term thing. And the materials and everything are all selected and coalesced to enforce that idea that we're going to write the exam, that all the participants might likely write the exam in the future. So it's more like a preparatory course. Thank you. Okay, yeah, thank you, Jinadeni. You see you're looking on the screen. I just hope so. I have uploaded it again for those who are joining us late. At the end of this training, all the people that have paid, I'm going to send us the Google link. There are some tables we're going to send you, the power factor table, the interest table. Tomorrow we'll be doing a lot of calculation. As Chima said, get your calculator, get your calculator standby and get ready, please. Very important. It's not going to be a theory. We've blended it to ensure that you also have the mathematics and the calculation side. I'm speaking, I'm not talking, so I hope you are solving your problem.
Richard, please, can you revert to slide mode? You're
okay.
In the...
Okay, this here we are.
Oh, okay, yeah, exactly. So like Engineer Uche rightly said, I mean, all what we're doing now, it's is the basics, like the title suggests, basic energy and electrical basics and all of that. By the time we go into industrial programs, we begin to do calculations for the conversion of electric energy into mechanical energy and all of that. It might look a little bit complex, okay? Just so that you try as much as possible to grasp this basic. We are going to be using all of them when we go into the higher level of calculation, which might be happening tomorrow or next tomorrow. So I think you can. I don't know if they've displayed the answer. Have anybody posted answer?
Let me check. Let me just sorry. No.
Nobody has posted.
So let's give them more. Let's give them more time.
The answer is D. I posted earlier.
Okay.
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 John said D. Okay. So let's proceed. Okay, just display the solution.
Sorry.
Go ahead. Keep going so that the answer comes out and all of that. Okay, so we have 160 and 120. Correct. To John that said D. So this is just the same thing with the other one that we saw. Just a little change of parameters here. Okay. So let's proceed. So this is power computational formula. Now we are done with the calculations on the power factor. Now let's look at the electrical systems themselves and the formulas for calculating the electrical equation. So we have the single phase AC system. So this is not too different from what we've done previously. So the P that you're seeing here is the true power, okay? Then is equals to the voltage times current times power factor. Remember I told you that your true power is actually determined at the point of consumption. So your voltage times current times your power factor is what actually gives you your true power. In this case, is in watt because we are talking about voltage, not kilovolt. Okay. So this is a formula to also behold. Where your P is your power factor from 0 to 100, then your V voltage and I is current. Okay, that's all. That's fine. Please go ahead. So I think there is a caveat here. In decimal form, power factor has unit. Okay. So if you remember that power factor has a formula. So if it has a formula, it should also have a unit, which is watt over VA or kilowatt over kVA. Okay. So that's the unit. But there's a purpose why this is being highlighted here. Now, for three-phase systems, you have something similar to what you have in a single phase, but in this case, you are now introducing the you're now introducing that is the cubic root of the power of you're not doing the cubic root of the voltage times current times power factor. Okay. Now that cubic root that you're seeing there is to take care of the three phases. Remember, you have three phases. So if you have in Nigeria, we have a standard by the NESIS regulation, we have a standard of 400 volts. But unfortunately, what we currently use now is 415. Okay, and I think that mistake is coming from the academic material that we use, which we are gotten from UK. In the UK, their nominal voltage is 415. So we take a cube root of that 415, we will arrive at 240 for each volt, for each line, yellow, blue, and red phase. But if you do 400, if you take a cube root of 400, you arrive at 230 volt, which is the volt of the appliances that you use within your house. Okay, so that cube root is to also distribute that voltage to the three lines that you have there. So that's the formula for the three phases, calculating the power, the true power of three phases. You have the cube root times voltage times current times power factor. And also note that the cube root, if you punch cube root on your calculator, you're going to have 1.732. So sometimes instead of putting that cube root, you can just replace it with 1.732 for ease of computation. Okay, let's proceed. So now this is an example. Calculate the power consumption for 10 ampere, 120 volt AC single phase electric resistant space heater. Can you people just give a try to this? This is just straightforward and very simple. You're looking at you're asked to calculate the true power. That is power of this electric resistant space heater. Okay, go ahead and click. Let's 1,200 watts. Okay, go ahead.
Okay. Hold on. Okay.
All right, exactly. So it's just straightforward. Exactly. Okay, correct. You all got it correct. So it's just voltage times amperage times power factor. Okay, and then you have your now the trick here is that your power factor is actually 1 because it's the resistance, is the resistive load. Yeah, so that's just the trick here, so that just to be sure that you pay attention to those details. Let's go ahead, please.
And it's not only resistive, it's also single phase.
Yeah, it's also a single phase. So you're not dealing with cube root here. So now this is a second example. Calculate the power consumption for a 3-phase 400. Remember, I told you that our system is 400 volt, not 415. But unfortunately, we have started using 415 actually. So now, calculate the power consumption for a 3-phase 400 volt AC 28 ampere motor with power factor of 87% at full load. Okay, so can we have a try on this? Michelle, let's proceed.
Okay.
16,876. Very correct. Okay, so the answer here is in kilowatt. You displayed your own in watt, so but it's all correct. Fine. So in this case, you have to now add your cube root, your voltage, then your amperage, then your power factor. Okay, to arrive your true power. So final. So let's proceed. Now we're talking about electrical demand load factor. Okay, so your load factor is actually the energy that you use divided by your P times time. Now this time here is assuming that you're looking at your load factor for a day. Okay, if you're now load factor is the amount of energy that you extract from a particular let me say a generator. If you have a generator, I just want to put this in a very simple term. If you have a generator of maybe 20 kVA and you're only using 10 kVA out of that capacity, okay, then your load factor will definitely be the 10 kVA divided by the 20 kVA. That is the actual peak capacity of that generator. Okay, so I'm putting this in the context of a generator, but in the in the slide here, it is being put in the context of a peak load. Okay. So your load factor is your actual energy, the actual energy that you use divided by the peak load times time. Now, this peak load times time is the total amount of energy that you can actually get out of that system. Okay, so that's what that means. So if you now take it, if you not take it to the end of it, you have kW average over kW. Okay, the first side of it is talking about energy, and the other side of it is talking about power. Okay, so your load factor can be in energy form, it can be in power form. That's what that means, right? So if you imagine the energy use of a building over a period of a month, the load factor would be blue area. If you look at the chart I have, the first one that I have, you see some portion are blue, while some portions are green. So the blue portion are actually the portion that you use. So imagine you have a luxurious bus or that can take 100 passengers, and you fill it up to the point of only 60 passengers. Okay, so your load factor, if that were to be your power system, your load factor would be 60 over 100. That's what I'm trying to explain here. So if you imagine that the energy use of a building over a period of a month, the load factor would be the blue area divided by the sum of the blue and the green area. A high load factor means that the building has a smooth usage profile. Without unusual spike in the demand, if all the equipment in the buildings was turned on and never turned off, the load factor would be 100. Now, what this is simply saying that if you have a peak demand of, now I'm trying to differentiate the foreign system and Nigerian system. If you're in America or in Europe, you're not talking about generator. You're talking about your peak demand, and you pay for your peak demand in the Western world. If you have contracted a peak demand of 50 kilowatts, every month you need to pay for that 50 kilowatts. It's different from your energy charge. But here in Nigeria, it is different. Okay. So that's why I keep it's more convenient for me to use generator as an example, so we can easily relate. Okay, because we are not charged demand, peak demand here in Nigeria. Okay. So, but what, like I earlier said, how you put this into perspective, imagine that you have a certain capacity of generator, say 20 kVA generator, and you're only making use of 10 of it, 10 kVA, okay, which means 50% of that generator is lying fallow, is not being used, okay, which means you can actually connect to your neighbors and then begin to improve your load, your demand load factor, okay. So in actual sense, that's what load factor is: the actual power or energy that you're taking divided by the possible amount of energy that you could have gotten out of it. Okay. I don't know if that's clear enough. Now, the reason why I have the other image by the right there is just for us to understand that, look, these things are not just straightforward. Okay. Your demand profile is not straight line. It goes up and comes down. So if you on your television, of course, it's going to go up a little bit. If you on your AC, it's going to go up a little bit. If you off your AC, it's going to come down. So it's not just straight. That's why I put that. So, and you see that the title of that chart is usage profile. That is actually true usage profile. So it's not a straight forward thing. And there's a caveat here that speaks to the higher load factor. So what that means is that the higher load factor will yield lower blended kilowatt hour cost. If you have a 20 kVA generator and you're using 18 or 17, depending on your power factor, what that means that you're putting that capacity to full use. And what that means that if you're selling the electricity from that unit, you're going to charge less. It's going to cost you less to produce electricity from that system than if you were using just about 10% of it or 10 kVA of that capacity. Now, the problem is that if you're using 10%, you have to recover the depreciation for 20 capacity. You're not recovering the depreciation for 10 capacity. Okay, so it's going to impact on your unit cost of electricity. And again, if you're burning fuel at 10 kilowatt, 10 kVA, you're not going to achieve the optimum value from that petrol that you're burning, but that generator is designed to burn higher fuel, so you're burning less fuel. So you're not going to achieve the best fuel efficiency at that level. So all of this will impact on the electricity output that you're going to get from that system. That's what that caveat is just talking about. When you have a higher load factor, you're going to have a lower cost of electricity production. Next slide, please.
Sorry.
Please, if anyone has any question, please, you can ask. So let's proceed. No, go back, please. So a low load factor means that occasionally the power usage is very high, but at another time it is very low. This building had a big spike. This makes the green area big and will result in a low load factor. Okay, so what this is just simply saying that if you look at the chart that I have by the right, to say, the one that has a little bit of a green on top of it, then blue and then the yellow. Okay, when you have loads comes on almost at the same time, or you have heavy load that comes on, you're going to create a spike on your profile. Okay, so what that means, if you have a 20 kVA generator, you can go as high as 18, maybe just like a few minutes, and then you come down again to about 12 or 10. So you've created a spike. Maybe you've added a heavy load that created a spike. Okay. Now that spike that you created is actually what is going to determine the capacity of generator that you're going to buy, even if you just created that spike only once in a year. Otherwise, if you undersize the generator and you create that spike, your system will go up. Okay. So it is important when you're sizing a generator, okay, you have to look at what could possibly create spikes and how can you eliminate those spikes, okay? So if you look at that load profile, okay, I talk about load shift, okay? You'll notice that there are some points you have a valley, then at some point you have a spike. Is it possible for you to initiate those spikes at the point where you have your valleys? So you don't create unnecessarily high demand or high peak load, okay? So that's what demand shifting is all about. You look at the points where you have a higher demand and you shift them, you push them to the valley where you have a lower demand, so you can have relatively a flat load profile. If you have a flat load profile, that's always the best, okay? So I'm just trying to illustrate how we can be able to manage spikes in our electrical system, in our load profile, how we can be able to shift demand from the time of from the time when you have high demand, move some of your consumption to the time when you have low demand, so that you don't have inefficient, you don't have necessary capacity that are lying redundant in your system. Let's go to the next. So this is just an example to make us understand the load factor. Compute the monthly load factor when peak is equal to 1,250 kilowatts. Energy used is 500,000 kilowatt hour. Of course, then time is 720 hours, 24 hours per day, and then 30 days per month. So what is going on? I'm seeing red.
I'm not the one doing it. I mean, somebody's playing around with the stream, but let's continue.
Okay.
It's not from my end.
Okay.
It happens once in a while in all this Zoom thing.
Okay. Okay, so the solution here is like, okay, if you look at the question, it tells you that your peak is 1,250 kilowatts, okay? And then your energy consumption is 5,000 kilowatt hour. So what if you remember the formula for our load factor, the formula for our load factor is the energy consumption divided by the peak demand and the hours or time, over the period that you want to determine. It can be a month, it can be a day, it can be a year. But in this case, we are looking at for I think a month. Okay, for a month. So if you're looking at the hours in a month, you have 720 hours in a month. Okay. So if you want to now compute your load factor, you have your the energy that you actually use within that month divided by the peak demand times the hours in that month. When you do that, you're going to arrive at 55.6%. Okay, so out of the 100% capacity that you have, you're only using 55.6, which is not bad. It becomes bad when it goes below 30%. It becomes very bad when it goes below 30%. Okay, so 55.6% is not bad. Now I'm speaking if you're using a generator. Okay, yeah, your generator becomes highly inefficient and wasteful when you're running it under below 30% load factor. Okay, so I hope that makes sense. Let's proceed. If anyone has questions, please do ask.
Not just question, maybe anything to add.
Okay.
You're free.
Okay, so we are gradually winding up. So you have degree days. Sometimes I know some of you may have heard about maybe heating degree days or cooling degree days and all of that. So I'll just briefly talk about that here. So degree days is a measurement of an absolute value, different of a daily mean temperature from a base temperature value. I'm having a little bit challenge reading because I'm doing this from a mobile device. Okay, but that's fine. Now a higher value of degree days means that the weather was more severe, either hot or cold, and more importantly, the more cooling or heating was probably needed to keep the space comfortable for the occupant. Now, what this is talking about, you can either have heating degree days or cooling degree days. But in Nigeria, what we'll have is cooling degree days, not heating degree days. If you're in a cold weather, you're talking about heating degree days. Now, what this degree days means that you have a base temperature that you're comfortable with. So, for example, you can say you're comfortable at 24 degrees centigrade. You're comfortable. Now, if the temperature goes above 24 degrees centigrade, meaning that you're going to cool from whatever temperature you have. So, example, if you have 30 degrees centigrade and your desired temperature, your base temperature is 24, or the weather temperature is 30, you're going to cool from 30 to 24. So, the difference between that 30 and 24 is your cooling degree days. So you have 6. When you minus 30, when you minus 24 from 30, you're going to have 6. Okay. So your cooling degree days becomes 6. Okay. Then if you're in a cold weather, maybe if you're in Europe or in America and the weather is very cold, then the reverse is the case. It becomes heating degree days. So if your base temperature is 24, okay, let me use the same 24, but normally they will have like 18. Okay. But let me use 24, for simplicity here. So if you have 24 as your base temperature and the weather is 18, okay, what that means you're going to heat up the environment to come up to 24 degrees. Okay. So now the heating degree day in that case now will become 24 minus 7 minus 18, okay, which will give you 6 as well. So that's what heating degree days and then cooling degree days is. You can compute this over 1 month, you can compute it over 1 day, you can compute it over 1 year. So it doesn't matter. It has the time varies. So let's go to the next slide where we'll show you illustration of how this is done. Go to the next one, please. Exactly. So this is just
will it be the last paragraph?
Okay. No, I wanted to go to the table. Let's do the last paragraph before going to the table. Okay, because this is just an example. So the one before the last paragraph, okay? So if we, based on what I've just explained now, if we consider a single day, so we're looking at just 1 day, and the temperature difference was 5 degrees above base, okay? Now that is 5 cooling degrees. Now this is just an example. If your temperature is 5 degrees above your desired temperature or above your base temperature, then your cooling degrees is 5. That's what that's implemented. Then the last paragraph is if we consider a week, okay, and on each day there was a temperature difference of 3. That's 3 degrees above the base. So if we have 24 and every day you're having 27, so the difference is 3, right? 27 minus 24, you have 3. That's what this one is. So for the 7 days, you have 3 differences. Okay. Now that will be for the 7 days times 3 for each day. So your cooling degrees will become 21, right? That's 21 cooling degree day. Okay. I don't know if that's clear. Let's go to the table. We'll have further example. Okay, so in this example, I've tried to establish the base temperature. So if we're in Nigeria, our base temperature will be 24. Okay, so if the temperature is 24, cooling degree days becomes 0. But if the temperature of the weather increases to 22, no, sorry, if the temperature increases to 26, right, then our cooling degree days becomes 2. That is 26 minus 24. I'm just trying to explain the base temperature here. The base temperature is the temperature at which you're comfortable. You want the temperature of your environment to always be at. So if the temperature is higher, you cool down. If it's lower, you heat up. That's what the base temperature means. Then if we are heating, if we're in America or in Europe, we want the base temperature to be 18. Okay. So if the temperature is minus whatever it is or 10, you have to heat it up to 18. Okay. So now on the table, I tried to do a weekly degree days. So if you look at the table, you have Monday to Sunday. Okay. Then you have daily mean temperature. So on Monday, you have 30. On Tuesday, you have 28. On Wednesday, you have 29. On Thursday, you have 34. On Friday, you have 32. On Saturday, you have 30. On Sunday, you have 33. Now, if you look at the HDD, that is heating degree days, we are not heating because the temperature is above, okay? So, but if you look at the cooling degree days, what that means that you're minusing the daily mean temperature from the base temperature, or rather the other way around, you're minusing the base temperature from the daily mean temperature. So if you minus 24 from 30, you have 6, right? That is for Monday. For Tuesday, you have 4. For Wednesday, you have 5. For Thursday, you have 10. For Friday, you have 8. For Saturday, you have 6. And then for Sunday, you have 9. So when you add all of this, then you have 48. So your cooling degree days for that week is 48. That's what cooling degree days is. Then if you're heating, it becomes a heating degree day. Okay? So that's it for the degree days. Let's go to the next slide. I think that's the last of it. Okay, so we've come to the end of this presentation, and I thank you all for your active participation and your contribution, which is very well appreciated. Thank you very much.
Thank you, Engineer Chima. I think it's question time. Thank you, Engineer Chima, for that very wonderful presentation. I would like to get some feedback from the participants. Can I have some feedback from the participants? And let me quickly upload the second slide, even though the time is fast spent, but I know it's worthwhile. So what we're going to do is the second slide is probably what I'm going to urge us to read through. There are no calculation inside, but I will just try to glance through it if we don't have question. Can we quickly go to the chat? And there's the second slide for today. The ones for tomorrow are going to be packaged in a Google Drive. So let me use the opportunity
which NA is raising up.
Okay, and you can go ahead, please. Question, feedback, contribution. Can we talk? Go ahead.
So please, I have a challenge here. I can't see anything in the chat box. You said you were going to post some things on the chat box. Sorry, I never saw anything in the chat box.
Well, that's a big challenge because I just posted one. Does any other person have that challenge? Can you kind of refresh your screen? But that won't be a problem. I think I will
just send one.
No, okay. You've seen one now. No, others said they don't have the same challenge. So no cause for alarm. Maybe you can just text me your email right away. But I know tonight. Let me. Chima, can you stop the recording, please?
Okay.
Please.
Okay.
Stop it so that we can download it and.